my name's Chandra Macauley, and my hometown is Billings, Montana, and I go to school at Montana State University, Bozeman. The title of my project, as you can see, is Understanding the Oxidation of Silicon Nanoparticles. Now, as far as why we'd want to do this, right now silicon nanoparticles are being looked at for next generation photovoltaics, and one of the problems with this is that they are not stable in solution by themselves. So you want to attach ligands to the surface, such as this. And one of those first steps, which I don't know if you can see here, is getting OH on the surface, so basically oxidizing the particles. This is one step that's not very well understood, which is why my project took form. What I did in my project was to try and understand that oxidation. And in the process of siliconization, we make our silicon nanoparticles and then expose them to washes and then oxidize them using water or nitric acid or hydrofluoric acid. And then go through a couple more washes, and then we silinize them, or basically put silicon with ligands attached to the surface. The main bulk of my project, I changed the exposure time to the oxidizing solution, so the nitric and hydrofluoric acid or the water. And I also changed the oxidizing agent. So there's a lot of ways that a silicon nanoparticle can oxidize. One of those being air, the solvents, water, nitric acid, or a combination of nitric and hydrofluoric acid. At each step of the process, both before and after oxidation, as well as after siliconization, I did various analysis techniques: photoluminescence, AFM, or atomic force microscopy, and Fourier transform infrared spectroscopy. Some of the interesting results, I won't go through all of them, but we found that photoluminescence shows us that the particles are actually being oxidized just by the washes. So we're using dichloromethane and ethanol to transfer the particles from toluene into a solution like ethanol that doesn't react with acids. But we found those washes are actually oxidizing our particles, which is not advantageous because our particles are already really small. They're like 3 to 8 nanometers, and so we don't want them to get too much smaller. We also found that there is a large difference in the particle size of nanoparticles that have been exposed to air prior to going through these steps and nanoparticles that had not been exposed to air. So you see these images, there are differences in the color as well as differences in the size of the nanoparticles in those solutions. The only difference is that these nanoparticles were taken out of the reactor, exposed to air, so they can grow the silicon oxide on the surface, and then they were washed with ethanol and DCM and then oxidized. And these are both exposed to the same concentrations of nitric and hydrofluoric acid, whereas these, they went straight from the reactor into the washes. So they didn't have that native oxide, which is one of the main differences we saw. And it's just a difference in the character of the oxide. The other thing that we saw was that the addition of HF creates much smaller particles that actually have higher quantum yields. And you can see visually in these AFM images that the HF produces much smaller particles, which is advantageous because with the higher quantum yields, you're going to get less defects, or that is a sign of less defects on the surface. So basically, just to wrap it up, we found, for one, that the solvent washes cause oxidation. For two, the presence of a native oxide definitely affects the particle size. Three, the influence of hydrofluoric acid in the oxidation definitely causes smaller particles and higher quantum yield. We would like to, in the future, for one, we need to get more results from quantum yields from the National Renewable Energy Laboratory and then analyze those. So those are some of the smallest particles that we have sent to them. The next step would actually be able to see, once you get down to a small enough size, it's no longer quantum confinement that dominates these PL spectra, but rather the surface states. And we'd like to see at what point that happens, like at what diameter that happens. And with that, that's pretty much my summer REU 2010 project.